I guess pretty much everyone's here. So we can get started. So the last time we were talking about, we started talk about dense paper and how he shows a lower bound for approximate policy iteration, where notably in the lower bound, he finds an example with some very simple features, very simple MDP, state aggregation, such that approximate policy iteration oscillates indefinitely between two not too great policies. In what way these policies are not great is that both policies have a suboptimality, which is shown here. And the notable thing is how this scales with 1 over 1 minus gamma. It scales with 1 over 1 minus gamma squared. The value function scale with 1 over 1 minus gamma. So even after normalization, you have an extra kind of horizon factor. This extra 1 over 1 minus gamma is there. And then we jump to me proposing that maybe we should look at this algorithm, this policy iteration with expert advice. Today, it was really funny. I was looking up the classic neurodynamic programming book of Pertzikas and Titiklis, and it has, like a chapter about approximate policy iteration, and I do have this thing sticking out. I don't know, you see it? Like these bookmarks. I look it up. It's exactly talking about this chattering phenomenon, and I have these notes there, I think from back in the day, that say that, well, if we would smoothen things, then this chattering would go away. And so here we go. This is Polytech. It's smoothing things. It makes the chattering, in a way, go away. Well, I don't know. Maybe it's still chattering. I guess we don't quite know that, but so it's proposition 6.2 and all the discussion of it. So there is the example. So Alex is asking, where is the chattering discussed? And there is the approximate policy iteration error bound. And that's proposition 6.2 in the book. And after that, example 6.4 on page 283 is the example with the chattering. But I think that this is the example that maybe Dan started from, and he improved it. And that is later, so the second bookmark is also about the chattering. So there is simulation in this book about, here supposedly the problem is solved with optimistic policy iteration. And page 323, you see this little like partitioning of the space, and then the note that, oh, the chattering will go away if smoothing would make the chattering go away. So that's page 323. Okay, anyway, so here we go, smoothing. And I'm not going to argue that whether the chattering goes away, but the point of the argument is that this additional smoothing that this algorithm is doing, its smoother updates, is going to result in a milder dependence on the approximation error. So the blow-up factor, this amplification, approximation error amplification factor, becomes linear in age. Age is just my 1 over 1 minus gamma, as opposed to being quadratic. And that's probably as good as it gets. we don't have a matching lower bound. We have argued for the square root d that has to be there in a worst case sense. I suspect maybe the age also needs to be there, but that needs to be seen, I guess. All right. What is this algorithm? And so we started the analysis the last time, but so today I want to finish the analysis of this, and if time permits, then also talk a little bit about the prospect of policy search and whether that's a good that's an approach but that's likely to succeed, or like we should manage our expectations regarding these procedures. But we'll see whether we get there. So what is this polytech? So you might recall that this is like policy iteration, but it's kind of a smoothened version of it. So in policy iteration or approximate policy iteration, you would have a policy, you evaluate it approximately, and here we assume linear function approximation. So this just means coming up with some coefficients. And for policy evaluation, we're going to assume that we have a G-optimal design available to us, and we have a simulator. And so whenever you need to evaluate a policy, you can just initiate rollouts of that policy from the points of the optimal design of a certain length. And if you make the length large and the number of rollouts per design point large, then we know that we can control the approximation. We can control how well we're estimating the action value function up to the approximation error multiplied with root d. So that's the policy evaluation part of it. So what you can do then is that you have your policy, you approximately evaluate it, you get this action value function. And then instead of greedifying, I guess like the proper way of denoting this is that, well, maybe for the second step, so here, okay, so pi2 is somehow obtained, you evaluate it, you get the second action value function approximation. And then when you come up with pi3, interestingly, you not only take into account the latest action value estimate, but you take into account both. So maybe there should be some line here too, right? So all the previous action value estimates are taken into account. The actual formula that gives you this is shown here. So you calculate this exponentiated sum of the previous action value functions. So this is the exponentiated sum of the previous action value functions. And then you just normalize. So you kind of treat this as a joint distribution, and you marginalize, and this way you get a distribution over the actions for every state. And one side note is that if you're using linear function approximator, then this sum can be pre-calculated by just summing up all the previous parameter vectors. So you can just maintain the sum actually, and when you get a new estimate, a new parameter vector, you just add it to the previous parameter vector, and then you just exponentiate and then normalize. Just a second. Okay. All right. So that's the algorithm. And okay, so since we are producing these policies, you might ask, are we taking the last policy? Not quite. I'm going to propose that we take the mixture of the previous policies. And this mixture is defined such that if you need to act, you just randomly select one policy and you follow it up to the end. You might wonder about whether this is a good idea or not. Is this going to have a high variance? Maybe you can do better than this. Maybe a weighted mixture is going to be better. I'm not going to care too much about this. Maybe there's going to be some homework about it. So the concern, obviously, is that, well, okay, maybe I prove that on expectation, and that's what I'm going to prove, right? That this policy that you get this way is going to its value function is going to be close to the optimal value function. But when you do this procedure and you do this calculation for n rounds, and then you randomly select one of the policies, maybe you're going to select the first policy. Well, the chances of that is 1 over n. If n is really large, then maybe you have nothing to worry about. But, if you are risk averse, maybe with probability 1 over n, you're selecting the very first policy, which may be a terrible policy. And who wants to keep following that terrible policy all the way? So you might be wondering about whether you can do better than this. In terms of the variance, so to say, it seems risky. Like with probability 1 over n, you are choosing a terrible policy, and maybe n is not going to be too large. We know policy iteration converges pretty fast. Okay, this is not quite policy iteration, but how large is n going to be? Well, it's going to be some number. Maybe it's still too large, and you want to be risk averse. You want to control, this bad event, and you might be worried about that. Okay, this is not giving just to that. That's a totally valid concern. But I'm just not going to address it here. Maybe save it for homework. I think it can be properly addressed. This shouldn't be much of a concern. Okay, so why do we take this average? Well, we take the average because it's just very nice and easy to deal with the average. It happens that if we, I should call this the mixed policy. We are mixing all these policies together. And so when you're mixing all these policies together, we argued the last time that the value function of the resulting policy is going to be exactly the average of the value functions of the policies involved. Okay, so that's good, because then if we need to control how big is the gap between the optimal value function and the value function of the policy that we eventually chose, then this boils down to controlling, this difference of this average of differences, right? So if we need to control v star minus v pi, then it's sufficient to control this average errors. And how can we control these average errors? You can bring in the value difference identity, and that brings in this big matrix, and so on and so forth. We did some manipulation, and we ended up with this identity. So notice that there were no approximations up to this point. So this is just an equality here. So we can decompose this error into two terms. And there is the first term, and then there is the second term. In the first term, and that's going to be the subject today, that kind of is going to be small if we're succeeding of choosing these policies that are as good as the optimal policy in maximizing, in choosing the actions that are maximizing these approximate action value functions. If we succeed in doing that, then we're done. So this is sort of like, I'm going to argue, so the term for this is that this is like a term that you control in online learning. This is a pure optimization term. So online learning is a generalization of classical optimization when you have some more general situation that we are going to talk about today, but it's basically optimization. And the other is, so this kind of corresponds to like how many iterations you want to do in policy iteration. As you do more iterations, the errors decrease. So this corresponds to kind of that. And the other term is it's coming from the errors because we don't exactly know the action value functions of the policies, but we are approximating them. So that's like the errors due to imperfect function approximation and imperfect knowledge and sampling error. So that's like approximation and estimation error as far as estimating the action value functions are concerned. Okay. So for the second term, that's easy to see that if you take the max norm of this term, you use the triangle inequality. Well, we know that the max norm of this matrix is upper bounded by 1 over 1 minus gamma. So that's the beauty of the discounted approach. And you can move in the max norm inside this sum. And then you can decompose it into the max norm of this difference of these two operators. And each of them is bounded by 1. And so the difference is bounded by 2. And then there is the max norm of the difference between the true action value function and the estimated action value function. So you arrive at this bound. And this is what we need to control. And here we just have to remember that in our previous lecture, we already control this by running this RSP procedure with this G-optimal design. So we have the error bound that is shown here. So assuming that the feature map is full rank, we can find this optimal design C, which has at most roughly d squared points, such that the action value function of the target policy is going to be approximated up to the accuracy that is shown here. So notably, the approximation error is blown up by a factor of root d. And then there is the estimation error, which has two parts. One coming from, because you're truncating trajectories, and you're summing up rewards up to a length of h along these trajectories only. And then there is the other part, which comes from that you have a limited number of trajectories per design point. So long story short, both of these can be kept small if you make h large, not too large. Then the first term is under control. The second term is under control if you make m large. So that's all good. And if you plug everything into this previous upper bound, then we see that we get 2 over 1 minus gamma times, so this epsilon pi infinity norm. So that's the approximation error when you're using the best possible parameter to approximate the action value function of this policy pi. And in this setting, we are assuming that the worst approximation error over all policies is bounded by epsilon. So I can just replace that with this epsilon. And then that gets multiplied with 1 plus square root d. Plus, we're going to get this square root d, and I can pull out this 1 over 1 minus gamma, and it's going to get multiplied by another 1 over 1 minus gamma and a factor of 2. And then what remains is this gamma to the power of h plus square root and then log. And here the coordinate of d is d times d plus 1 over 2. And so the 2 cancels, and then I get this bond. Right, so the first term is nicely under control. So it remains to bond the second term. And okay, so if you're gonna have n iterations, then and we need to control the error with high probability over the n iterations, we can do that by using a union bound. And if we're truncating the estimated action value functions to these interval, then by the usual technique, you can bound the expected error, so the expectation of this error, by 2 terms. It's going to be delta naught, which is the probability that you run an error event, times 1 over 1 minus gamma plus this other term that is written over there. So in terms of the expectation of the second term, this is the bond that we're gonna get, right? So here the randomness comes because Q hat is random, right? Okay, so in terms of controlling the first term, so what is this? So this is the sum. And maybe it's worthwhile to specialize this to a specific state. If you fix a state, so this is a function of states, right? Like this is a big vector. It has as many components as the number of states, and for any specific state, the value of 1 at that state, that's a weird notation, is the sum of if, let's say, the optimal policy is I don't know, deterministic policy, then this would be just q hat of k at s and pi star of s. Otherwise, I would need to write a sum. I'm just expanding the definition of m pi star. Minus, and then q hat of k s, and here I need to sum over all the actions and weight them according to the policy that we chose, this pi k. So this is how it looks like. You can write it in many different ways. Yeah, I will write in some other way to emphasize some linearity that is somewhat hidden here, but we'll do that soon. So just to understand what's going on here, so every iteration k, so for k goes from 1 to up to n, what happens is that we need to choose a policy, a pi k, a distribution over the actions for every state. And then we do this computation to compute q hat of k that may depend on the choice of pi k, right? Like it does depend on the choice of pi k because we're evaluating pi k. Okay. And after this is done, then we need to somehow establish that we are able to control these deviations, right? So we are, in a way, if you think that Q hat of K is approaching Q star, then pi star is going to choose the best action at that state. You need to compete with the best action. You need to gradually get better and better at betting on what the best action is. And thinking about that, okay, this exponentiation, it somehow selects the best actions intuitively, right? So it's like if eta is pretty big, then it definitely just selects the best action, right? Like eta goes to infinity, then these policies become the Dirac policies that choose with probability 1 the action that is maximizing the resulting expression. If there are multiple of those, then any distribution works. But here, the proposal is that somehow we shouldn't quite do that. So the proposal is not to let eta go to infinity. If eta was infinity, this is almost like policy iteration, except that we are still summing up the action value functions. Summing up the action value functions, you could say that, well, that should reduce the variance or something like that. It's somehow not part of the proof to show that that effect is exploited in any ways. Maybe a better proof would exploit that, but we are focusing on the dependence on the approximation error, and in terms of that, we are already done. Like so, if so this term shows the required dependence on the horizon, so we're done with that. And we are pretty lax in controlling every other term, including this term 1. So if we can make this go to, not if we can make this grow faster than linear in n, then we will be happy. So recall that this term 1 is divided by n. So if for example, we can prove, and this is what we are aiming for, an upper bound on this term, which scales with square root n, then you get the square root n from here. Sorry, you get the square root n from here, and then you divide it with this 1 over n, and so altogether the first term is going to be 1 over 1 minus gamma over root n. And so if you're making n large, then you're done. And if you are shooting for some suboptimality gap of delta above the approximation error, then, you know, like 1 over delta squared iterations is going to cut it. Scale with horizon. Fine. Okay. So is this how is this working? But before that, do you have any questions? Is everything clear?
What is the expert advice here? The expert advice. The name was policy iteration with expert advice.
It's coming. Right.
I have a quick question. So you mentioned that if eta goes to infinity, then we're doing policy iteration. Can you
Not quite, right? But almost, yes.
Can you explain more, like why that's
okay? So it's not quite true. I said almost true. So what would be policy iteration? So what's okay? So there are many variations of policy iteration. So there is a variation of this algorithm where pi k would be chosen just to be proportional to eta exponentiation of the last action value function. This one. Okay. All right. So this is the abbreviation that pi k of a at the state s is proportional. So it's just normalization of the exponentiation of eta times q hat of k minus 1 s a for every of the actions. And now, if you think about it, what happens as eta goes to infinity? So if one of the values, so let's say you have a number of values, the q values here, and they are that ordered. So the first value is the largest. So this is the first value is the largest, and then there is the second value, and then there is the, I don't know, the third value, and then let's say 3 values suffice. Okay, this is the third value. And then you're exponentiating them. So exponentiation, what does it do? So if you take the exponential function, so this is e to the x. Here's x. It tends to, you start with a value x, and it's going to push it higher. And the higher the value that you're starting with, the more you push it. Okay. And when you're doing this normalization, so when we normalize this, then the normalization allows you to say that, well, I get the same distribution no matter how I shift up or down these values, right? So if I add a constant here, a c constant to all of these values, the probability distribution that I get at the end is going to be the same, right? Why? Because we add this constant here, so that results in a multiplicative effect of multiplying the previous values by a number. So it seems that like we are, like multiplying all the values with some number. But then we are normalizing, right? So we are summing everything with respect to the actions. And so there we are also multiplying because we just added the constant, and now we are normalizing the shifted values, and therefore this cancels. So the probability distribution that is computed is invariant to shifts. So this means that you can shift these values anywhere you want. So you can make sure that the smallest value is at least 0. So that means that all the values, this is the smallest value of q smallest, right? And all the other values are somewhere on the non-negative axis. And I have a certain range, and this is the largest value in terms of action values for a fixed state. Okay. And then you see that, well, okay, this largest value is going to be enlarged much more than the smallest value, right? And this difference just gets larger if this scale is increased. And what does eta do? Well, eta is increasing the span, right? If you make eta bigger, the span between the smallest and the largest value is going to be larger. And the similarly, the span between the largest value and the second largest value also gets much bigger. And because of this, after normalization, what you see is that the probability of the action that is maximizing these values gets closer and closer to 1 as eta goes to infinity, right? So no matter what Q hat values you started with, this is what's happening. Assuming, let's say, for the sake of simplicity, that you have a unique maximizer. Okay. Is this clear?
Yeah, thank you.
Okay. So that's okay. So then that kind of explains why this is related to policy iteration, because policy iteration would just shoot for this maximizing value, right? To circle back to the original question. And so we see that there are two differences. We're kind of not doing quite policy iteration. We're taming it down by choosing an eta, which is maybe not that large. We don't know how large it should be yet. The second thing is that we're summing up all the previous action value functions. That's also some kind of taming stabilization effect. So all of these two things are acting towards stabilizing policy iteration. All right. That's a good question. Okay, so how do we handle this this term? So here the important thing is that, okay, like for every state, we need to control these terms. We want to control the L infinity error, the max norm error of these terms. And so that means we need to control these errors state-wise. But if we can control the errors state-wise, like the sum of all of these errors at every state is controlled by the same absolute value, no matter what the state is, we will be done. So we can as well just fix one state and focus on what happens at that state. And now we're gonna also forget about the particular details of how this Q hat of K is computed. And the only thing that we need to remember is that this Q hat of K is going to be computed. And after that, we do this truncation. Remember, I said we should do the truncation. And because of that, it's just going to, like, these values are going to lie in this interval of 0 to 1 or 1 minus gamma. So now we can think about the meanest way that Q hat of K could be computed. So then the game is something like this. For every iteration, you choose a distribution. So if you fix a state, then all what we are doing is just choosing a distribution over the actions, right? So fixing a state allows us to rewrite the game as follows. We can think about this as a game played between someone who is choosing the distributions and someone who is choosing the functions. And for every round of this game, the learner chooses pi of k, which is going to be just a distribution over the actions. Okay. And then sometimes the part is to forget about the details. So this is one example. We're just going to think that the adversary can choose Q hat of k, which assigns a value to every action. So this is going to be a map from actions to reals, but we limit the adversary that the the largest possible value that it can assign is 1 over 1 minus gamma. Okay. And we need to control how much we regret of not following some distribution. And now I'm going to go back to a notation that emphasizes more the linear nature of this process. So we are asking the question, does there exist a way of choosing these distributions if you are the learner, such that no matter how the adversary reacts to these choices, the adversary can be reactive. You can control this expression, by which what we mean, recall that this is going to be divided by n. And if after division this goes to 0, then we are happy. So we want this to be sublinear, little o(n), right? So Rn divided by n should go to 0 as n goes to infinity. Right. So nothing really happened here except that I switched the notation a little bit because I just fixed one state. And now I'm not denoting the dependence on the state anymore, because we have to control this expression for every state. So if we can show this in general, then for every state, repeat the same procedure. Things are going to work out fine. Okay. So the problem, so this is standardly called regret. And this problem is known as online linear optimization. This has a name. This is a problem that has been studied before. And it is a special case of online learning, which is a subfield within machine learning, where you have this game situation, this sequential situation, that there is a learner who proposes some decision variable. In this case, this is a distribution. This lives on the simplex, right? So this is a probability distribution over the actions. But you can generalize this to the case where the learner chooses a decision point. Usually, people study this in the convex case. In the convex case, the decision point is in a vector space, in a convex subset, convex non-empty subset of a vector space, usually closed, bounded, sometimes not bounded. And then there are different interesting subcases. And then the adversary is choosing something like a payoff function. So here, Q of k is the payoff function, and it has some meaning to us. But people who study online learning, they just say, okay, like the adversary is just choosing these payoff functions. And then you want to compete with whatever other decision point you can think about. So here, the important thing about pi star is that we are not making any specific assumptions about it. For every pi star, no matter how pi star is chosen within the simplex, we want this algorithm to control this regret. Okay, so the adversary may be shooting itself in the feed by choosing payoff functions such that this pi star is not maximizing the sum of these payoff functions. That would be bad for the adversary. We will still control the regret. Kind of the worst case for the learner is when pi star is the best possible choice for the payoff functions that are chosen in a reactive way. And the payoff functions, so in general, they are, okay, so here we are maximizing, so these functions would be concave, but in online learning, people look at minimization, and then these two guys would be swapped, and you would be talking about convex online optimization or online convex optimization. And instead of payoff functions, you would talk about loss functions, and they would be convex. And so in that case, you have a sequence of losses that are maybe chosen in this reactive way, and X is maybe a subset of a Euclidean space, and I don't know, convex, probably closed. And you still want to control the regret. So the regret in this case is against some X star decision point. The regret is going to be like, how much is your total loss versus how much the total loss would have been had you chosen from the beginning of time this single point X star. So competing with the best, competing with a fixed decision in the hindsight, maybe it's the best, maybe it's not the best. X star could be, like you want to control this for any X star. It could be the best that minimizes the sum of these losses. The nice thing about online learning and online convex optimization, so this is like a little sales pitch, is that it generalizes many things, and it's widely useful in a wide variety of context. So it generalizes convex optimization. So in convex optimization, all these losses could be the same. The same loss. And you're just optimizing. And the sublinear regret just means that, well, you're making progress in optimizing this function. And it somehow expresses things like that. Okay, maybe you could be optimizing with just gradient information. It has parts where it doesn't, like, things don't have to be convex. So even non-convex optimization can be modeled this way. Some parts fit. It has implications for learning, how fast you can learn. It's useful in a wide variety of contexts, and it's just a beautiful subject. So here these LTs would be convex. So what's the convexity in our case? Well, it's concavity because we are maximizing. So these functions are just linear functions, right? So we can think about these as a function that maps every point of the simplex to a value, right? So take the function that takes a point of the simplex, pi, and it's mapped to the inner product of pi and q hat of k. How does this depend on pi? What's the name of this dependence? Yeah, it's linear. And linear is in a way, it's good and bad. Linear is really good because it's both convex and concave. It doesn't have curvature, so that kind of makes things a little bit silly sometimes. So as opposed to, like a quadratic loss, if you have linear losses or linear objectives, then things can be pretty wide. So if you want to control this regret, then if we greedily jumped on each time on like the best possible thing in hindsight, so the learner can choose this pi k the way they want it to be chosen. So they could go for like, oh, I've seen these previous functions. Okay, so maybe I just sum them up because I need to compete with the best in hindsight. Pi star could be the best in hindsight. So my best knowledge about what could be the best in hindsight is that I just sum up all the payoff functions that I have received so far, and let's maximize with respect to that. That's my pi star. So that would be jumping to corner of the simplex. Now, that is a bad strategy, right? Because then the adversary could just like do something like, oh, the simplest case when you have a simplex is when you have two actions, and that's just the 0-1 interval. And then the adversary could go in and say that, well, let's first choose this function. Well, okay, this function. All right, so payoff. Okay, after seeing this function, we want to choose this. And then the adversary goes, oh, let's choose this one. It's exactly canceling the previous one. Okay, my drawing is not perfect. So before, when the learner chooses this point, the adversary chooses this function. So the learner receives a payoff of -1 or something like that, right? This payoff here, right? I was unable to draw it in a nice way, but it should be nice and geometric. It's like if this was +1, this was -1, this is going to be -1, this is going to be +1. And so the adversary has the power to choose the payoff functions after seeing the choice of the learner. So if the learner makes a stupid choice like this, then the adversary is just going to be like, haha, I'm going to exploit you. And after this is done, then the learner, okay, so maybe the adversary should do it in such a way that if it knows that the learner is going to be greedy, then it wants to mislead the learner to choose the other option a little bit. So maybe this is tamed a little bit. This is -1 plus epsilon. That's and then this is +1 minus epsilon. That's the very first function. The second one is, I don't know, like -1 plus epsilon over 2. So this point is still going to be preferred, and then this +1 minus epsilon over 2. And now, after seeing this, then the learner jumps on this one, and then the adversary can flip back and then keep halving things. And every time, the learner is going to suffer a huge loss. Whereas if, like, you sum up everything almost always cancels. And the best point is going to be in the middle, where everything cancels. So the best point in hindsight has a value of 0, and the learner is suffering a loss of 1 compared to this in every round, basically, right? So this learner that jumps on things is not good. Just being too greedy is not helpful, especially in an adversarial context. So what can be done is that you kind of slow down things a little bit. And that's where the strategy that I was talking about comes in. And for this strategy, the following theorem is known. So if pi k is selected as proportional to the exponentiation of eta times the sum over these things, these payoffs, then the statement is that the regret is going to be bounded. So no matter how the adversary plays, no matter how pi star is chosen, the regret is going to be bounded by 1 over 1 minus gamma times 2 n log a. So this 1 over 1 minus gamma just comes from the fact that we were scaling the scale of these functions where their range was between 0 and 1 over 1 minus gamma. So that's their span. In general, that's the span that you would see from there. And where does the log a come from? So it's kind of like a halving strategy that we have here. And if there was a perfect choice, then the majority voting learner would learn with log a mistakes, but there is no perfect choice. So therefore, the majority voting, the generalization of softening of that happens to be this multiplicative update, or this rule is also called the multiplicative update, or this exponentiation rule, or Boltzmann strategy. Yeah, I'm not going to prove this theorem. The proof of the theorem can be found in many sources, including the blog on bandits, but there is a very short proof. And it just uses some algebra, and it's not that insightful. That proof that's given there, it's a very short proof. That's the advantage of it. If you want something really insightful, then I have lecture notes about online learning, where I kind of build up all of these from the elementary majority voting and all that, and like how the softmax is multiplicative updates are generalizing that, and why all of this makes sense. An alternative way of proving all of this is to realize that this is a special case of online learning, online convex optimization, and then online linear convex optimization refers to the case when these LTs are just linear. So LT of x can be written as I don't know, x in a product between x and a yt, and the adversary just chooses a yt. So that's the case. And for online linear optimization, you have these two algorithms, follow the regularized leader and mirror descent. You might have heard about them. And they are more like algorithm schemas. So they have some free parameters in them. It's kind of like a regularized kind of notion. And the proof that uses that that machinery maybe is a little bit more insightful, because it also leads to you know, other results, and like why this form you can ask questions about, and it has quite an elaborate theory to it. So maybe I just show you how this is the same thing as mirror descent. Maybe that's well. Or at least, what do people mean when they're talking about mirror descent? And when they talk about follow the regularized leader. Follow the regularized leader is the easiest to explain. So the claim is that this algorithm is at the same time an instance of this general algorithm schema that's called follow the regularized leader, and also mirror descent. It's a special case of both. In general, these two algorithms do not coincide. They're different. In this case, they happen to be coincide. They happen to be the same. And follow the regularized leader is easiest to explain by first talking about follow the leader. And we already talked about follow the leader. So if we talk about this, if we consider this online convex optimization framework, so here we are minimizing things, then follow the leader there is the algorithm that in round T would choose the minimizer of the losses that have been received so far. This is follow the leader. And this is actually the algorithm that I criticized here, because this is the jumpy algorithm that if the adversary is ugly, then this can, with the linear losses, it can suffer a linear regret. Whereas it's possible to get this sublinear regret with the smoothed versions of these algorithms. So with linear losses, this is not a great choice. If the losses do have some curvature, though, this may be an okay choice. So, for example, you have losses which are quadratic. It's like linear prediction with quadratic losses, or favorite, least squares. Okay, you can model it in this framework. That leads to losses with some curvature. Even in that case, you're better off adding a little bit more curvature, but just very little. But if you had real curvature, okay, least squares, linear least squares is not a good example for this. So you have to add some additional regularization there to get things under control. Otherwise, like, there is this subspace problem, that there is information that you haven't seen in the subspace, and then you can still suffer a big regret because of that. But if you have like quadratic losses which are curved in every direction, so not lie in a subspace like in linear prediction with quadratic losses, then FTL is not a bad choice. But okay, for linear case, this is not a good choice. And then the next best choice is called follow the regularized leader. So in follow the regularized leader, you're not doing much but adding one extra term. So there is this function R that maps points of X to reals. It's called the regularizer. And you usually choose it to be a nice convex function. And eta is a learning rate parameter. Oh, here, I didn't say what eta should be. We'll have to get back there. So eta is a learning rate parameter, and its choice comes from analyzing the properties of this algorithm. And this algorithm happens to be a pretty solid algorithm for good choices of eta. The idea is to prevent the jumping around by kind of just adding, like just a homing term that kind of, pushes you towards a benign place. That place where this R pushes you should be a guess about what should be the optimal solution. But if you have no idea, then like, okay, people choose 0 or whatnot. Well, these days, everything's a lot of meta learning. There, people would choose, like, let's learn what would be a good guess of what decision to take based on previous tasks, right? Then you can regularize towards that. So there are connections to meta learning as well, if you wish. And you can get better bonds if you do this. And then you were right about the guess. So that's FTRL. And the next algorithm is mirror descent. It's a little bit hairier to explain, but it's kind of very similar to this previous algorithm. The difference is that, well, this algorithm synthesizes all previous losses by just summing them up. The reason it's doing it is because, well, we need to compete with the best decision in hindsight, which corresponds to the sum of all the losses. So far, we have only seen t-1 losses. So our best guess of what the total loss could be is this partial sum. Mirror descent algorithm doesn't quite do that. So the mirror descent algorithm says that, well, I should choose xt based on only the most recent loss. So but I also want to prevent jumping around. And the way we will do that is by adding a term that will make us stick to our previous decision, to the vicinity of the previous decision. So there you add a term that is similarly derived from this regularization function R that makes you stick to the previous decision. So there are two ways of stabilizing, basically, and then you can combine the two, and like people have done this. And there are pros and cons of doing it this way and that way. But so one way is just summing up everything, so that summarizes all the past. So that's here, and then just add the little stabilizer and minimize. So that's regularized empirical risk minimization, if you wish. And the other one is more like the gradient descent style, where you have a previous iterate, and the new iterate should be the result of solving for the minimum of the most recent loss. The previous iterate doesn't incorporate that loss yet. So I add that loss, but I want to stay close to the previous iterate. And this term here, this dr, is called Bregman Divergence. And it's around xt-1. And this is basically the Bregman divergence induced by this regularization function. And this is just this function that you would get if you take the remainder term in the first order Taylor approximation to the regularizer function at x based on doing the Taylor approximation at xt minus 1. Okay. So the Taylor approximation of Rx based at xt minus 1 is that I have to take the value of R at xt minus 1 plus add to that the gradient of R at xt minus 1 times the deviation between x and xt minus 1. So that's kind of like the best linear approximation based on the Taylor series expansion up to order 1 of R. And if you want a picture, this is how it looks like. So you have xt minus 1, and the best linear approximation. Oh, I will try to draw a better figure. The key to drawing good figures is not to scratch too much and not to stretch too much. Okay. Not so simple. Okay, so this is xt minus 1. This is the linear approximation. So this is R of xt minus 1 plus gradient at R xt minus 1, x minus xt minus 1. And this is just Rx. And so R was a convex function. So what's shown here as kind of shaded for every value of x, you get this difference between the function and its best linear approximation. If you have a convex function, then these linear approximations are lower bounds for the function. Therefore, these are non-negative. So this is a non-negative valued function. It's also convex in X. How do we know that? Well, R was convex, so these regularizers are convex. R was convex, and a linear expression is convex, and summing something two convex functions gives you something convex. So back to our case. So this is mirror descent. The reason this is called mirror descent is because you can solve this in 2 steps. I'm not sure I want to go into that. So in our case, X is the simplex on A. So these are all probability vectors. Okay. That's our X. And the Bregman divergence inducing regularizer is a negentropy. So, okay, so maybe P is a better letter here. And it turns out that after a little calculation, you can calculate that the Bregman divergence induced by R on a simplex happens to be the KL between P and Q. And even better, you can solve explicitly this. If you take P on the simplex. Just stick to the notation that I used before. And then here you plug in the KL between P and P of t minus 1. Then you get this multiplicative form update, which tells you that PT of A should be proportional to PT minus 1 of A times, okay, if we are minimizing, it's going to be e to the minus eta and yt of A. And if you're maximizing, then so if this mean was a max, then that would be a plus, just flipping signs. Okay, you have to believe me on this. It's just calculation that you can also do. But this is also a recursion. So this previous guy was obtained the same way and so on and so forth, right? So you can imagine that maybe you initialize P of, is it 0? It's P1 in my notation. That's a bad choice. To be 1 over A, then what you get is that PT of A is going to be, if you unroll the recursion, then this is going to be proportional to e to the minus A times y, oops, sorry, this is t minus 1, this is t minus 1. Yt minus 1a plus and so on and so forth up to y1a. Okay. There are situations where it's worthwhile to not to start from the uniform distribution if you have some prior knowledge about where the optimum could be. That corresponds to using a weighted regularizer. But we don't need that at this stage. Okay, the point is that this has the same form as what we have, and therefore, case proven, our algorithm is mirror descent. Of course, I didn't show any of the intermediate calculation steps, but I just claimed that that's simple algebra. Well, or maybe not simple, but like you can calculate this. This is a constraint optimization problem. How hard can it be to calculate the solution of a constraint optimization problem? Can be hard, but in this case, it happens that you have a closed form solution. And so one justification to use all of this is because we have this closed form updates. This regularizer, this negentropy regularizer, is not really the best possible that you could come up with, even for the simplex. On the simplex, it's pretty good. If you would switch to something like the squared loss, sorry, not the squared loss, the squared regularizer. So you switch to something like RP is, I don't know, 1/2 of the 2 norm squared of P or something like that. Or maybe it's like you want to center it around the center of the of simplex. It doesn't really matter. Your regret is instead of depending on log A, it's going to depend square root log A. It's going to depend on square root A. That's not good. Although there are some, anyways, it's a long story. It's a long, complicated story. There could be some advantage of, like, sometimes you want to give up on this logarithm dependence in order to gain something else. It's a fascinating big topic. Okay, so going back to where we have been, so we have this theorem now, or you have to believe me that we do have this theorem for this algorithm. So no matter how the Q hats are chosen, this is true. So that is super, right? That's fantastic news, because then, okay, where were we? So we were left with controlling term 1. So now we see that term 1 can be controlled by 1 over 1 minus gamma times 2n log a. It's never larger than that if we follow this recipe that I talked about. All right, so what's eta? Well, eta is going to be square root log a I guess 2n 2. And everything has to be scaled with 1 over 1 minus gamma. So with the specific choice of eta, this term is controlled by, so the first term here is controlled by the square root 2n term, and we're going to divide that by n, multiply it with 1 over 1 minus gamma. You add everything together. If you want the data accuracy, then you can choose n to be 1 over 1 minus gamma times 1 over that squared, 1 over 1 minus gamma squared, because that is 1 over 1, oops, that is 1 over 1 minus gamma from here. Or maybe on cube, because this is going to be squared. Anyways, it's some polynomial function of 1 over 1 minus gamma and the inverse square of the target suboptimality level scaled somehow with the logarithm of the number of actions. And the other terms are similarly can be controlled. You can put everything together and you get a result that is very similar to the approximate policy iteration result, except that now the approximation error dependence is much milder. That's the point. So, did we win? If we care about the approximation error, then this is definitely a win. Altogether, if I calculate the total cost of the procedure, the first term in approximate policy iteration, that would be a geometric term or something like that. So the number of iterations n in approximate policy iteration doesn't have to be large. There was this gamma to the power of, I don't know, n dependence that you need to make as small as data. And so that's like a really fast dependence on the target accuracy. So here, the target accuracy is data, then you get 1 over data squared. That's like a polynomial dependence on 1 over data. So that's exponentially slower, exponentially more iterations than in policy iteration. Okay, so altogether we do more simulation, but it's still polynomial. It's just like a higher order polynomial in all the quantities of interest. Okay, because the data already impacted like how much work we have to do here and here. So there was already a 1 over data dependence on approximate policy iteration as well. So now we have a higher order dependence. It's a bit bad, but it's maybe not the end of the world. And in exchange, we are gaining on the scaling with the approximation error. And you might ask the question, okay, is this inevitable? Is the computational bound the best possible that we can get this way? I have no idea. No one gets anything better. I know that, but I don't know. It's a fascinating open question. So we don't really have matching lower bounds. So let's say you demand that the procedure shows a scaling on the approximation error like this. You can ask the question, okay, what is the best possible runtime result, runtime complexity result? We just have upper bounds. We don't have lower bounds. All right, so that's the end for today. I guess next time I'm going to talk about policy gradients. It's inevitable now. It has to come. All right, any questions?
What was the better regularizer you were suggesting for online learning instead of
it's based on the square root, the sum of the square roots of the absolute values of the coordinates. It's called Salis entropy.
So how do you spell the first names?
It's let me write it here. Salis.
Okay, thanks.
You're welcome. Salis entropy has fantastic properties. Removes logs, allows you to interpolate between the stochastic and the adversarial setting. Yeah, it's beautiful.
Wait, so why don't we use that here if it's
because
better?
It's computationally more expensive, and it's easier to state that you do softmax and like, yeah, with all the caveats that okay, this may add an additional log, may not be optimal, but you know, people love this thing, love entropy.
Right.
Well, this is also entropy, but it's a different entropy. That's like the next level. And another way you can make things better, by the way, if you're talking about that, is that, you know, like this process of selecting the Q head of case, it's not that adversarial, right? Like we are learning these, and we are slowing down, and these are close to each other probably, and getting closer to Q star if you're lucky. And maybe there is a lot of additional regularity that you could jump on, and then you could design even better algorithms that exploit this. So at one point, we completely like forgot about all the details, which is like a strength, but also could be a weakness, because maybe you can achieve much better results by keeping in mind those details. Also, Q head of K, the span of those may not be as large as 1 over 1 minus gamma. So what if, like, you know, all your value functions lie in 0, 1? Well, of course, you can scale them with 1 over 1 minus gamma. But if you didn't know in advance that that's the case, then you need to choose the learning rate parameter, or you decide you don't need to, right? Like, but you want to simplify things, and then you say, I know that, like, okay, truncation, like I can choose the learning rate based on a prior idea of the range. I can get the result, but it's going to be highly suboptimal compared to the best that you could get if you have a small range. So you can have these adaptive algorithms which exploit a lot of the regularities that come from the special properties of these sequences. And not much of this is actually explored in the literature. So it's quite, I think it's quite fascinating of what possibilities may exist here to make these algorithms better. Also, I didn't mention that, like, some people would identify these algorithm polytech with PPO or whatnot. I don't like that, because I think that they are different algorithms. The other algorithm has the KR reversed, and like maybe they have constraints rather than these regularizations. So these differences actually do matter a lot. Like, I wouldn't be able to necessarily prove the same things with the reversed KL, and if you put constraints here rather than the regularization, like, I don't know how the proof would work in that case. So you gotta be careful with this, but it's true that, like, there are lots of variations of this. That's another reason, like, I bring up this exponential form, is because you see it everywhere and people love this thing. And I think that this is a very clean, simple way of thinking about the benefits of doing all of this. Although you have to recognize that there are a lot of details here, right? So it's like you're summing up all the previous action value functions. It's not just like you take the very last one. That wouldn't necessarily work. So it's, yeah, details do matter.
Is the idea of smoothing out the policies related to conservative policy iteration?
Yeah, it's also related to that, right? Like, conservative policy iteration is based on the idea, like the same thing, that, okay, you don't want this chattering. You want to make safe bets on how to improve your policies. And I think that this is like a clean implementation of conservative policy iteration in a way. It's not really doing the same thing, but it's like it's the same gist.
Like, you mean because you don't have to store like all the policies and all that, or?
Well, it's okay. Here you are lucky because you can sum up the parameter vectors, so you're not storing much. That's true. It is still choosing randomly one policy at the end, which is bad, which we talked about a little bit. So in a way, you store, right? Like, because you will need to, okay, you can do this incrementally, this random choice. Actually, you can decide about which policy you're going to follow before generating all the policies. And then you just stop. And if you were lucky, then your computation is going to be totally cheap. Well, lucky in a, okay, you're unlucky because your index is low. So your policy is going to be crappy, but you're lucky because you're saving a lot on computation. So you can do this incrementally and like very cheaply. I would probably not do that. I would probably just at the end, like we have this average policy, this mixture policy. I shouldn't call it average policy. I want to call the policy that's the average policy that's averaging the distributions over the actions, like state-wise averaging, right? Like state-wise averaging is different than taking a mixture. So this is a mixture policy. So you can take the mixture policy and you can learn its action value function. Maybe you can just be greedy with respect to that. And that should tame the issues.
Wait, sorry, could you repeat that last point? What was that about? Learning the value function.
So the average policy is a policy. You can learn its value function up to this approximation error or whatnot, and you can just greedify with respect to that.
Are we talking about the average policy or the mixture policy?
Sorry, mixture policy.
Oh,
Yeah,
mixture
the
policy.
average policy, we have no control about how good that is.
Right.
Alternatively, you don't need to do any of this if you're cleverly exploiting that Q hat of K are not arbitrary. It's not an arbitrary sequence. So that's known as the question of the last iterate convergence in mirror descent. The last iterate is going to be a good point to play, or you have to take an average, or maybe you have to take a weighted average after the last points. So all of these are possibilities. Yeah, I don't know whether I would be able to prove that, but I have the suspicion that maybe the last iterate is not terrible here. Again, experimentally, it seems to work.
Okay, but in some cases, like for some reason, the last iterate might be worse.
Oh, like we know that in linear optimization, linear online optimization, if you don't care about how these payoff functions are generated, the last iterate is a terrible idea. You have no control.
Yeah.
Huh?
Okay, okay.
Because in online linear optimization, it's like being greedy, so not good.
But wasn't the result we just had telling us that the average regret would go to 0 eventually? So wouldn't
The
that
average
mean...
regret goes to 0, but that corresponds to playing the average policy, playing the mixture policy. Sorry, I keep saying average policy, but playing the mixture policy. That.
Oh, okay, okay.
Yeah. All right, I better go.